In this section, we're going to continue on studying inverse trig functions. We'll start off with a couple of questions that are similar to the ones you would have seen in the video notes, just to kind of get warmed up, and then we'll look at some new types of questions. So for examples 1 and 2, definitely want you to pause the video and try both of these yourself to kind of see how well you're understanding how to evaluate inverse trig functions. All right, so in this first one, right, we're taking the inverse cosine of the negative square root of 3 over 2. And the key here is always remembering that what does an inverse give you? It gives you an angle, right? So what we're looking for is an angle so that if you take its cosine, you get the negative square root of 3 over 2. All right, but the key here is that the cosine inverse will only spit out very specific things. It only spits out angles on the top half of the unit circle, right? Or from 0 to pi. So in this top half, when will the cosine be negative root 3 over 2? Well, that's going to be over here, right? So we, of course, know that that is 5 pi over 6. So we can say theta equals 5 pi over 6. Or in degrees, of course, 150 degrees. Now, are there other angles that give you negative root 3 over 2? Yes, right? 7 pi over 6 would do the trick, but it is not between 0 and pi, right? So we've got to remember, cosine inverse only gives the upper half of the unit circle. All right, tan inverse, right? So we're looking for an angle so that we get this when we take the tangent of that angle. All right, now let's remember what values the tangent inverse spits out. So remember, it's going to only spit out values on the right half of the unit circle. Okay, now what you want to do when you see things like this with tangent is ask yourself, okay, where on this half of the unit circle am I going to see special values that involve 1 and special values that involve square root of 3? Because we remember that the tangent, of course, is the sine over the cosine, right? So we need to make this 1 look like it is one of the special values, so I could divide it by 2 to make it a half. And that's okay as long as you divide the bottom by 2 as well to make it square root of 3 over 2. All right. Now, of course, we want it to be negative, okay? So in the right half of the unit circle, that's going to happen when you let the y value be negative. So the negative goes up here. So where is the y negative a half, or the sine negative a half, and the cosine root 3 over 2? That would be right here at negative pi over 6 or negative 30 degrees. All right, and then example 3, right? So we're going to now do compositions of inverse functions with trig functions. All right, so stop for a minute and think about what you think the answer should be to this one as well. So we're going to take cosine inverse of the cosine. Now, if you think back to Math 141, when you take the inverse of the original function, you usually just end up with the input coming back as your answer. We got to be a little more careful here, though, because our cosine inverse only spits out certain values. So what we want to do is just go ahead and take the cosine of 7 pi over 6. So doing just a quick sketch of a unit circle, 7 pi over 6 is right here. So the cosine, the x value, is clearly going to be negative square root of 3 over 2. All right. Now this is the same thing we answered back in example 1. And we know that the answer to this is not 7 pi over 6, it's 5 pi over 6. So the moral of this story is just to make sure that you understand when you compose a function and its inverse, just be careful. It's not necessarily, it could be sometimes, but not necessarily going to be the number that starts inside that inner function's argument. All right, so on the next page here, let's look at example 4, kind of a similar thing happening. So we have the tangent inverse of the tangent of pi. So on our unit circle over here, okay, the tangent of pi, well, pi's right here, okay? So the tangent of pi is the sine of pi over the cosine of pi, which is 0 over -1, which is 0. So this is going to be the tan inverse of 0. Okay, but if I'm taking the tan inverse of 0, right, then I'm saying that that means I'm looking for the angle so that the tangent of that angle is 0. But we again remember that tangent inverse only spits out values between -pi/2 and pi/2. So our answer to this is not pi, but 0. Now let's do the composition in the other direction. So the last few we've taken the inverse of a trig function. So now let's take a trig function of an inverse trig function. All right, so the first question is, if we have the sine inverse of a half, right, that is an angle. So we want the sine of that angle to equal a half, right? Do we know that angle? Well, yeah, because 1/2 is one of our special values, right? So again, sine inverse is only going to give us values between -pi/2 and pi/2. So this is going to be the tangent of, all right, so then the angle that's going to give us a sine of a half is here at pi/6. So I get the tangent of pi/6. Okay, but then the tangent of pi/6 is, of course, the sine of pi/6 divided by the cosine of pi/6, which is 1/2 over the square root of 3/2. Running out of room there. Which is equal to 1/2 times 2 over root 3, which would give me 1 over the square root of 3. So when we recognize a special value for sine or cosine or tangent or whatever inside of here, then we want to use that special knowledge just to go ahead and then write that inverse as one of our special angles and then just evaluate. But that's a different setup than what we have here in example 6. So as I look at example 6, and I want to take the sine of the cosine inverse of 4/5, 4/5 is not one of our special values. So we can still start thinking about it similarly to the last problem, right? So the cosine of 4/5 is equal to some angle, which means the cosine of that angle is 4/5. But on the unit circle, right, 4/5 is not a special value for cosine. So what that tells me is I don't want to think about this in terms of the unit circle in order to get a nice exact answer. So let's remember the other way to think about trig functions is to think about them on triangles. So here I'm going to sketch a triangle and do something like this. So a right triangle, of course, where this is my theta. Now remember that a cosine is adjacent over hypotenuse. So that means I can, as I draw this triangle, 4 can be the adjacent side, 5 can be the hypotenuse. But if I know two sides of a right triangle, I can always find that third side, right? So if I call this y, I can say 4 squared plus y squared equals 5 squared. So y squared is equal to 9. So y is equal to 3, right? And technically it'd be plus or minus 3, but of course we're not too worried about negatives here. So we've got y equals 3 as our y. So here's what I can say. I've said that I'm thinking of this cosine inverse. This is just an angle on this triangle. So when I rewrite this, I can just rewrite it as the sine of theta, right? I just replaced cosine inverse with theta. But now I can see what the sine of theta is just by looking at this triangle. It's the opposite, 3, over the hypotenuse, 5. So my answer here is just 3/5. All right, so let's take a look at example 7. So we're being asked for the cosecant of the tangent inverse of 5/6. So I look at that tangent inverse of 5/6, and 5/6 does not ring a bell as a special value at all. So I'm going to set that equal to my angle, which means the tangent of that angle is 5/6. And so as I draw a picture here, tangent, I know, is opposite over adjacent. So I label this one as 5 and this one as 6. And so of course I can find that x there. So x squared is 6 squared plus 5 squared. So x squared is equal to 61, so x is the square root of 61. So when we take the cosecant of this, we're really taking the cosecant of the theta that we've drawn in the triangle. Okay, but cosecant, remember, when we're talking about triangles, is hypotenuse over opposite, right? It's the reciprocal of sine. So hypotenuse over opposite would be the square root of 61 over 5. Now the one other type of problem that we want to be able to look at is the one in example 8 here, where same idea as what we were just working on, but they don't necessarily give us numbers to work with. So I want to take the tangent of the sine inverse of 2x. All right, so we'll start as we did the last ones. Let's try to make sense of the sine inverse of 2x. What do we know about it? It's equal to an angle, which means the sine of that angle must be equal to 2x. Now at first it might not be clear how we make it look like those other ones, because those other ones we had, the sine of an angle or the tangent of an angle equal to a fraction. But don't forget that anytime you don't have a fraction and you want one, you can just make one artificially by saying 2x over 1. And we know that that should be the opposite over the hypotenuse. So my picture can be something like this. Here's my theta. Opposite is 2x, hypotenuse is 1. So if I want to figure out what this is, let's call it a, I can say a squared plus 2x squared equals 1 squared. And then I can get my a squared all by itself. So a squared is equal to 1 minus 4x squared. So a would be the square root of that. So with all that, I can then come back up here and say, all right, we're going to take the tangent of theta, because that's what sine inverse of 2x is equal to. But that is the opposite, 2x, over the adjacent, square root of 1 minus 4x squared. And that would be my answer.